whole narrative that we have that someone out there, that alien man, or just to be facetious, alien man is seeing what's going on Earth. He's probably seeing what dinosaurs are doing or something, right?
Yeah.
So if hypothetically there was somebody far, far away and he was trying to see light coming from the Earth, and he was like, I don't know, 100 million Earth, he would not be seeing the current Earth, right?
Yeah.
See,
whatever. Yeah, so dinosaurs died 65 million years ago. And if you look at what is 65 million light years away, it is our nearest cluster of galaxies, the Virgo cluster. There aren't too many galaxies in between.
Okay.
So we are talking of even bigger scales, right? So there wasn't much on the Earth where most of the galaxies are. Actually, there's a very interesting concept of something called the radio universe. See, our radio transmission started in the 1920s, right? Now think of, so about 100 years of radio and then television has gone out. And actually people can pick up these things. So if there are aliens, so people have mapped the number of stars that are there in a sphere of radius 100 light years. There are quite a few stars, about 1,000 stars in that volume. And there will be planets around them.
Yes.
So you can think of somebody now tuning in to, I don't know, I Love Lucy or something like that, watching it on a planet that is 50 light years away, right? Or watching Groucho Marx or whatever, something like that, these early television series or the original Akashvani. That is possible, right? I'm not sure about light, because light is quite faint in terms of whether they could see what's happening on the Earth. So yeah, the aliens existing billions of light years away, moot point, they'll never get to us.
Yeah.
Even somebody who's 50 light years away, if they're watching I Love Lucy, to get to us will take a long time. Right?
So all these alien invasion theories are not scientific, ultimately.
Probably
the
not.
Huge OTT industry around.
Probably not.
Thank you.
Yes. I don't know whether... I'll go where the mic is going, yes. Yeah. But you can...
All right,
yeah.
Quick question. This has a lot of mathematicians and physicists in this economics department. If in the first 10 to the power of minus 47 seconds in the universe there are no laws of physics that we can explain, shouldn't there also be no laws of physics after the universe is 10 to the power?
Total. Yeah,
So
absolutely.
what's your speculation on what laws existed before and after?
No. I can't speculate because I don't know. That's the only thing I can say. The thing is, that it's not just 10 to the minus 47. In fact, actually, even longer periods, the period in which gravity had to be quantized, we don't have a theory for it. We don't have a theory for quantum gravity. And that is why one of the reasons is that it's very difficult for us to predict the evolution of the very early universe. Same thing will happen here. What we're talking about, say 30 billion years from now, when the universe is so sparse that the galaxies are very far away from each other, the objects that we know of as objects now will be all ripped apart, because space itself is being ripped apart. And so we'll go back to these elementary particles, and you'll go back to the regime of the same regime as you were. To some extent, it's a cyclical thing of gravity being dominated by quantum effects. And so unless we get to a stage where there is a theory of quantum gravity, you don't know. And so I can't speculate. I can't even speculate, for example, where a lot of this dark energy comes from, because a lot of that would have been generated in the early universe. It is true, one of the things that I didn't tell you, I didn't go into the last recent research in this, is that we now know that dark energy has become really important in the last half of the age of the universe. Before that, dark energy was not as important as matter. And the fact that the universe has expanded so much, the effect of matter has gone down and the effect of this dark energy has gone up. That's telling us something. So it is through finding out some experimental features of how these things evolve, we get clues about what these things are. That's telling us something, but I don't know what it's telling us. So you have to ask this maybe 10 years, 20 years from now? And this is why I'm glad to see so many young people in the audience. I hope there are people here who will ask these questions later on. And so this is the magic of science in a way. I mean, this is how you move. This is a paradigm shift in science. It just went completely unexpected in a direction where people, can't even explain what these things are. So I would rather not speculate, but point out that this is really one of the interesting connections between the early universe and the late universe. I think they are governed by very similar physics. Yes.
Wonderful talk. I couldn't help but notice that you completely avoided the mention of, even though you talked of Hawking, the quintessential poster child of astrophysics, black holes. Was that deliberate or?
No, I mean, this didn't come here in a way because I could have given you a whole lecture on black holes,
okay,
or something else. In fact, I came a few months ago to give a lecture on black holes in SPS. There is a connection with black holes here, and the thing is that the Big Bang itself is a singularity. It is a time at which you can't really describe the physics, and the inside of a black hole is of course a singularity. So there are similarities, and Hawking of course worked a lot on not just Big Bang but also on the early universe and how these singularities are very similar. There's a whole Hawking-Penrose set of work which looks at applying the same kind of physics to the early universe as you do to black holes. So the black hole story is not really connected to the dark matter, dark energy explicitly, and that's why I did not mention it. But eventually, if you want to understand the nature of singularity and the nature of the Big Bang, you can't avoid it. Yeah.
And another quick question is, if the universe is expanding, what is it expanding into?
Yeah, that's a very, very good question. And of course, it's hard to answer that question for two reasons. One is, of course, the answer is we don't know. As we don't know what was there before the universe started. But it is more subtle than you think. And that is, we're now thinking of the universe expanding in a kind of three-dimensional way, right? But the universe is actually four-dimensional, because space and time form four dimensions. And since our conception is very three-dimensional, the way we are thinking of that expansion is not really the way it is happening. Now think about it this way. This is Carl Sagan's famous analogy of, think about a two-dimensional creature on a three-dimensional sphere. So there are ants that don't know how height works. It can only go in two dimensions. Now, if you let it loose on an apple, that ant will just go round and round, not knowing that it's a finite object. Right? Because it doesn't have the perception of the third dimension. Similarly, your question is, what is this thing expanding into, is based on the assumption that it's a three-dimensional expansion, right? However, it is not. And so mathematically, the whole reality is four-dimensional. And if you look at what it's expanding into, to some extent it's expanding into itself, right? Because there is the fourth dimension, or there might be higher dimensions that you can't visualize, right? So that's the thing. And actually there is this idea that there could be, of course, parallel universes, universes that exist outside our universe and things like that. But that's a different question. There was a question there also, but please go ahead. Yeah.
I think what you're talking about is the nature of matter, right?
Yeah.
That's what I think you were coming to. When we think of superstring theories as explaining what matter is, then it's either 13-dimensional or 27-dimensional.
Something like that.
The dimensions are all curled up. How does that fit in with what you were saying in terms of the expansion?
So,
what are we expanding into, and so on, perhaps then into all that?
So this is what I was alluding to. I mean, I think the reality of dimensions and how many dimensions there are is a feature of this our understanding how gravity works and how gravity is quantized. And the superstring theories are ways of understanding the quantum nature of gravity and also how the universe would have started and the early universe and things like that. So that's where the connection is, not much more, because if the universe is indeed 13-dimensional, even in the Randall Sundaram models or M theory and things like that, 9-dimensional, those other dimensions would have curled up at the very beginning, right? It can only be used to explain inflation and the early universe. It doesn't have much effect on modern day universe and its future. However, I think that once we understand the true nature of dark energy, we have to invoke this understanding of the early universe and also string theory, because that will help us understand the nature of dark energy, because that's where it originates to some extent. That's the connection I see. Otherwise, I don't see the connection of what we do now in terms of the experiments that we carry out now with string theory. Yeah.
Can we take a couple of questions from students before we wait for 2 minutes?
Yes.
So first of all, I would like to say thank you very much. Your lecture was very inspiring, and I love the fact that you managed to tell us how astrophysics developed, and how you also mentioned how it was through your lecture. I thought that it was very decolonized, and how Indians have also had major roles in figuring out microwave. Also, the role of female scientists in the 19th century that led to all this development and so forth. But my question is, since I belong from the discipline of geography, and I deal with that particular period of 2.6 million years of the Quaternary, which you showed in the geological time scale, and also with another discovery by an Indian person, Dr. Lal, and he used to work with terrestrial cosmogenic nuclides, basically silica, being rocks, and how they interact with the cosmic rays and create all of these TCNs on the surface of the Earth. So my question is that is the rate of the incoming cosmic rays have been similar throughout the history, at least in the quaternary history that we are looking at, because mostly we are not dealing with primary rocks.
That's very, very interesting question actually, and I'll tell you why the answer is no, and the answer is actually there is a lot to be learned from geography and geology and the history that is there in the rocks in the earth, and studying the difference between the earth and the moon, which is why I'm so excited and I write so much about our exploring the moon, because the earth and the moon were formed at the same time, and yet the features on the surface and the core of the earth and the moon are very different, because they were formed similarly but at similar times when both were fluids, but they hardened in different ways. Now, the earth, what I didn't show you was that, of course, the stars are going around in the galaxy. I showed you how the galaxy is. And the sun has gone around in the galaxy 20 times in its lifetime. 4.5 billion years, and it's 220 million years is its time it takes to go around the galaxy. You saw how many features there are. Those spiral arms, and the earth, along with the sun, goes through all those features and has gone 20 times. Now, over millions of years, of hundreds of millions of years, as the earth is traveling through all these features in the galaxy, a lot of things happen. People have said that the dinosaur extinction feature its history in its rocks and its geography that needs to be explored. I mean, all these lakes that you have, which are essentially formed out of asteroids hitting us, can be correlated with some time when the earth was somewhere in the galaxy, right? This hasn't been done. So there's a wonderful way geography and geology can come together with astronomy. There's a good reason why the Royal Astronomical Society in England actually caters to both geologists and astronomers. It's a society together. And the presidency of the society alternates between a geologist or geographer and an astronomer, because this is actually recognized as a connection, though it is not very well articulated.
Thank you, sir.
So, my question is, in special relativity, the speed of light appears as a fundamental limit on the propagation of information and the causal influence. So, why does this maximum speed arise as a property of the space-time itself, rather than being just a feature of specific to the electromagnetic waves?
It's actually not, because as Maxwell showed, I mean, studied Maxwell's equations, it turns out as a fundamental constant that comes related to the propagation of electromagnetic waves, right? So it's a fundamental constant that's connected to the propagation of electromagnetic waves when you look at electric fields and magnetic fields working together to produce light. That has nothing to do with space-time. And this is why the special theory of relativity, which was published in 1905, first postulates this as a feature of the speed of light. The general theory of relativity, which comes 10 years later, links it with space-time, but not in a way where space-time itself tells you anything about the speed of light. They are two different things, right? The theory of gravitation and theory of electromagnetism are decoupled. They don't. So when I showed that light propagates through space-time and it follows space-time and the contours of space-time, what is changing the contour of space-time is gravity. But what is causing the light to travel through the universe is disturbances in electromagnetic fields. And that is different from each other. So there is no explicit connection in the two. However, of course, they get connected because we use light to probe all these different things. And so we have to understand the relation between the two. And this is why we use light to probe gravity. But they're not fundamentally connected.
Maybe one last
question? Yes.
Yes, sir. Good evening. Good to see. Lecture was very good. So, sir, my question is direct. Why we can't travel faster than the speed of light?
Yeah.
Suppose if we travel faster than the speed of light, so whatever was Lucy was doing on Earth, so the information is traveling the speed of light. If we travel faster than the speed of light, so we'll be able to recognize what was happening in the history of
Yeah, absolutely. I wish we could. I mean, I really, this is of course the stuff of fantasy, as you know, and the stuff of science fiction. It just turns out, the answer I just gave, it turns out as a consequence of modern physics, mostly the theory of electromagnetic waves and also the special theory of relativity, that essentially says that the maximum speed you can attain is the speed of light. And it's very interesting is that you can't add anything to it. So for example, if you are delivering a cricket ball and you run very fast, your ball will pick up your speed as well as the speed of your hand, right? But if you are flashing light from a torch and you're running with it, the speed of light stays the same. Nothing you can add. So that is a very odd consequence of the nature of light. And that's what the fundamental principle of the special theory of relativity is. Now, every consequence of that initial assumption of the special theory of relativity has now proved to be right. So we think that the theory of relativity stands as it was, and you really can't add anything to the speed of light. Now, that doesn't mean 100 years later somebody is going to find something that will violate that, but till now that comes as a fundamental feature of physics, and I wish we could break that, because if we really have to explore space the way you see most of science fiction do, we really have to go at very high speeds. We can't.
It's my privilege to propose the vote of thanks on the 28th Krishna Bharadwaj Memorial Lecture. We are deeply honored to have Professor Somak Raychaudhury today, and his insightful lecture beautifully illuminated the wonders of the universe, combining depth with clarity and making complex ideas not only accessible but also engaging. We're grateful to Professor Raychaudhury for generously making time to be with us today and sharing the knowledge and perspectives he has. I thank Professor Sunanda Sen for sharing her memories of Professor Krishna Bharadwaj. I would also like to thank Ranjan Roy's uncle and aunt who have come here to be with us today. Of course, we're deeply indebted to the university administration for continued support of the Krishna Bharadwaj Memorial Lecture, which enables us to bring distinguished personalities from a wide variety of areas to our academic community. In particular, I would like to thank our Dean, Professor Vivek Kumar, for his efforts in reviving this distinguished lecture series after a gap of almost 8 years. Finally, I would also like to thank the organizers, CSP faculty members, staff in CSP office and the Dean's office, and of course our student volunteers who work tirelessly behind the scenes to make this event successful. We of course sincerely appreciate the enthusiastic participation of our guests and audience members who added great value to today's event. Finally, we pay our respect to the legacy of Krishna Bharadwaj, who was a distinguished scholar, a beloved teacher and mentor, and an institution builder for excellence, and above all, an excellent human being. So with that, I thank all of you and close the session. May I request all of you to join us for the tea served outside.